Okay, in this chapter we're going to talk about solving linear inequalities, well actually systems of linear inequalities. So you should already know how to solve a single linear inequality, but if you don't, let me go ahead and show you what you can do. If you want to solve a linear inequality like 2x minus 3y is less than or equal to 6, basically what you want to look at is you want to look at the corresponding equation, which is actually a line, and I call that the boundary. And now in order to find in order to graph the boundary, this line, you know that you can, most of the time you can do this with intercepts. So simply let x be 0 and solve for y to get the point 0, negative 2. Then let y be 0 and solve for x to get the point 3, 0. And so you'll notice down here I plot the point 0, negative 2 and the point 3, 0. And notice that I drew a solid line through those 2 points. Now it's important to note that the line is solid, because here you'll notice the inequality has the equal to sign with it right here, but over here this one doesn't. So if you look at this one over here, you'll see I didn't draw a solid boundary, I drew a broken boundary. So that's the difference. Now on these linear inequalities, which is what we have here, you've got to decide if you are going to graph above the line or below the line. And it turns out all you have to do is just pick any point on the Cartesian coordinate system, as long as you know which side of the line this point lies on. You know, is the point going to be above it or below it? Now generally the easiest point to pick is the point 0, 0 right here. So as long as the line doesn't go through 0, 0, I can use that line to check. So this line is actually above the graph. And so to determine if I shade the same side as my test point, I simply plug the test point back into the inequality. So go back up here to the inequality and let's see what you're going to get. You're going to get that if you plug 0, 0, you're going to get that 0 is less than or equal to 6. And then you just say, is that true or false? Well, that's true. So when your test point gives you a true statement, that's the side you're going to shade. So you can see that I've shaded everything on the same side as the test point. So that means all of these points over here will make that inequality true. And and remember, that also includes all the points on this boundary line as well. Now my second example uses the same boundary. So I'll use the same intercepts, 0, negative 2, and 3, 0. But since it doesn't have the equal to, notice I drew a dashed line. So I would have a dashed boundary. Now, again, I can test 0, 0. But when I plug 0, 0 into this one, it'll actually give me 0 is greater than 6, which of course is false. So since I got a false statement, then that means you shade the opposite side of the line. So you shade below the line. Since 0, 0 was above it, we got a false statement, we shade below the line. So you can see I've got all the points below the line shaded, and none of the points on the line satisfy the inequality. Before I move on, let me just explain to you what it means to say x is greater than or equal to 0. Basically, if you're saying x is greater than or equal to 0, then your boundary would be the y-axis here. I meant to do a straight line there. Hang on. So the boundary would be the y-axis here. So this would be the boundary, the y-axis, and your points would be all the points on the y-axis plus all the points that are greater than 0, where all the points where x is greater than 0. So that would be all the points on this side. Now obviously if you did less than or equal to 0, it would be the other side. Okay, and notice I used a solid boundary here because it says greater than or equal to 0. If it just said greater than 0, this would have been a broken boundary. Now, here, this says y is less than 0. So basically what I've done here is I've actually made an error here, and let's see if I can fix it for you real quick, because that should be a broken boundary since it doesn't have the equal to. So let's make it a broken boundary. How's that? Okay, so that's a broken boundary. Maybe we can see it better if I change colors here. Okay, I think you can see that better. So the boundary here is a broken boundary, and because the line y equals 0 is the x-axis. And if you want to know where y is below or where y is less than 0, that's actually going to be below the x-axis. Now, what's interesting is in business applications and social science applications, it generally turns out that our variables have to be non-negative. So we're going to see a lot of this happening, where both x and y are greater than or equal to 0. Well, where x is greater than 0, you know, is to the right of the y-axis, and where y is greater than 0 is above the x-axis. So where those two inequalities intersect is just in this first quadrant. So the solution would be this darker region here that I've got identified in the first quadrant. And of course, since they say equal to 0, it also includes the axis here and the axis here. So it includes all the points on the axis. So we're going to see a lot of this later when we solve more problems. Okay, now I'm going to solve this in 2 steps, but you really don't have to use 2 steps. This is a system of linear inequalities. Now what I'm going to do is I'm going to graph each one of these inequalities just the same way I showed you in the previous steps. So this one, the boundary would be 2x plus 3y equal 12. And if you let x be 0, you get y equal 4. Let y equal 0, you get x equals 6. So the intercepts are 0, 4, and 6, 0. So you'll notice that I made sure the line went through 0, 4, and 6, 0 here. And notice it's a broken line because up here I don't have the equal to. Alright, so then I'm going to test the point 0, 0. So if I plug 0, 0 into this first inequality, I get 0 is greater than 12, which is false. So that means I shade the opposite side. Now 0 is below the line, so that means I got to shade all the points above the line. So that's how I got that shaded region. Now the second one, 2x minus y equal to, if I let x be 0 and solve for y, I get negative 2 for the y-intercept, and then if I let y be 0 and solve for x, I get 1 right here, and that's the number 1 for the x-intercept. And now I just draw the line through there, and notice this line is a solid line because this inequality had the equal to with it. And then I can test the point 0, 0, and notice when I test 0, 0, I get the statement 0 is less than or equal to 2. Actually, it should say less than or equal to 2, but it's still true. So it's a true statement. So notice that 0, 0 is above the line, and I got a true statement, so I shade all the points that are above the line. So that would be, all these points I've got shaded here. Well, now, to actually graph the system of linear inequalities, you kind of put these two regions together and look for the overlap. So here's one line. So remember this line, went kind of through here, and then this other line, was a broken line, and it went through here. And what you want to do is find where those two regions that we shaded earlier overlap. So remember, we had to shade for this line, we actually had to shade this side of that line, and then for this line we shaded this side of that line, and so the overlap would be this dark green area. And this boundary is going to be a broken boundary, whereas this boundary is going to be a solid boundary. So that's the region. So all the points in this dark green area would be the solution. Okay, so now I'm going to just kind of slowly go through the next example, and I'm going to leave this for a practice problem for you to do, and I'll just kind of summarize it for you. So I have 2x plus y is less than or equal to 10, x plus 2y is less than or equal to 8. So I took the boundary. Notice I graphed the first boundary here. I plugged in the test point 0, 0, got a true statement, so I shaded the same side of the line that 0, 0 is on. Then I wanted to graph x plus 2y equal 8, so I graphed the line x plus 2y equal 8 here, and I tested 0, 0, got a true statement again, so I shade everything below that line. Well, if you put those two on the same graph, it'll look kind of like this. So I had everything below this line shaded, and I had everything below this line shaded. So you see this dark green area, that represents the entire region. Now something that's going to be interesting that we're going to see in a little bit later, when we bring in the fact that x must be greater than or equal to 0 and y must be greater than or equal to 0, it's actually going to bound us here and here, so we'll just get this quadrilateral. Now that's not what we have yet, but that's where we're headed. Okay, here's a more complicated system, and this time I'm using x1 instead of x2. I mean x1 and x2 instead of x and y. If that bothers you, just go ahead and change the x1 to x and x2 to y when you work the problem. But just know x1 is x and x2 is y. Okay, so the first one, I'm going to do this just like I did before. I'm going to identify the 3 boundaries, and then I'm going to find the intercepts of the 3 boundaries. And I think you know how to find the intercepts by now. So the first boundary, when x is 0, y was 6. And I'll say x and y just because it's easier to say instead of x1 and x2. And when y is 0, x is 12. So that goes through here, 0, 6, and 12, 0, and it's going to be a solid boundary. And then I can test this point 0, 0, and I got a true statement. So you can see I shaded everything below that line because that's where 0, 0 is. Okay, well the next one goes through 0, 7, and 7, 0. Those are the intercepts. So that one would actually, okay, ignore these points. I should have highlighted this one. So this is the point 7, 0, and then this point up here, which you can't really see, is the point 0, 7. And so I had to draw this line through those 2 points. But then I tested 0, 0, and when I plugged 0, 0 back into that inequality, I got 0 is less than or equal to 21, which is a true statement. Well, then the third one, it goes through 0, 10, and 5, 0. So what I had to do was I had to take this one, and I'll tell you what, before we do that, let me explain something to you at this point. At this point, we've got, if you look at the overlap at this point is the dark green area. Okay, so the dark green area is the overlap at this point. But now I'm going to bring in this third inequality that goes through 0, 10, which is right here. Where is it? There it is. 0, 10, which is right here, and it goes through 5, 0. But what's going to happen is when I test 0, 0 this time, I get a false statement. So that means I've got to shade the opposite side. So if I shade the opposite side for that line, then remember this dark green region that I had before? Well, this actually is going to come in and it's going to make that dark green region, it's going to make it just be this dark purple region right here. So let me see if I can show you here. Hang on just a second, let me pause. So the final solution here, you can see these red lines, those are the boundary lines of that final solution. So it's kind of a triangle, but it extends forever and ever in this direction. So that's what we call an unbounded region. All of them have been unbounded so far, but that would be an unbounded region. So that's pretty much how you solve systems of linear inequalities. You just graph them and find where they overlap. Now, there's a reason we need to do this, and one of the reasons we need to do this is so that we can find solution regions for linear programming problems that we're going to get into. But before we do that, we need to talk about something called corner points, which is just the vertices of the region, and we'll do that in the next video.